Okay, so last time we talked about the epsilon delta criterion. Okay, so this is the theorem we finished at the theorem. The theorem says, okay, f is continuous at x equals a, which is equivalent to say that f can satisfy the epsilon delta criterion at a. Okay, so this theorem gives you a new definition for the continuity at a. That means that says, okay, f is continuous at x equals a if for any epsilon greater than 0, delta greater than 0, there exists some delta greater than 0, such that for x minus a is less than delta. That means that x is very close to a. Okay, if x is very close to a, then less than, how close it? Less than this delta, then this the function values would be very close to f of a, which how close it is described by less than epsilon. Okay, no matter how small epsilon you have, you always have this delta. So when x is close to a, less than delta, the distance between ax and a is less. The absolute value means the distance, right? The distance between x and a is less than delta, then the function values would be the distance between the function values f of x and f a is less than this arbitrary small epsilon. Okay, so this is called the continuity. So this is a way, one way you have seen in your calculus book, which is called the epsilon delta criterion definition. Okay. So now we want to say, so in our textbook, okay, we start from the sequence, right? The sequence, terms of sequence, then to define a continuity, right? So now we set up the equivalence. So we needed to prove that the theorem that says, okay, we have two these two definitions, these two things are the exact thing, right? So we use the if and the only if. So we need two directions, right? Okay, so let's prove it. Okay, so let's look at this direction. This direction means we know that f is continuous at x equals a, as defined in the terms of the sequence, okay? Then we want to know does f satisfy the epsilon delta criterion. Okay. So suppose f is continuous in terms of the sequences. What does this mean? This means suppose limit n approaches infinity of f of x n is equal to f of a if xn approaches to a when n approaches to infinity, right? This is the definition for the continuity in terms of the sequence. We have a sequence which is xn. The sequence has the limit a. Then the new sequence, which is f of xn, this new sequence also have the limit f of a. Okay, so then we say it's continuous, right? This is the definition in terms of the continuity, the definition of the continuity in terms of the sequence. So now we want to prove that this f satisfies the epsilon delta criterion at a. So it's not easy, right, to do that directly. So we can use the contradiction. Okay, we suppose this f does not satisfy the epsilon delta criterion. Okay. So the problem is, so when you say does not satisfy the epsilon delta criteria, so you need to convert this one into our math language. Okay, what does this mean? What's the meaning for does not satisfy? Okay, so last time we talked about the things. Satisfy means for any epsilon greater than 0, there exists a delta, right? Such that for all the points in this interval, the f of x must be less than this epsilon, right? F of x minus f of a is less than epsilon. Okay, so now we need to say, okay, everything becomes the negative, okay, the opposite, right? So it means what? It means, i.e., what does this mean? We need to convert this one to be our math language, right? That math language means, okay, there exists some epsilon 0. Okay, we can use this one or epsilon. We'll just say there exists some epsilon which is greater than 0 for any delta greater than 0. F of x minus f of a should be greater than or equal to this epsilon for not for any x, for some x, such that this x minus a is less than delta. Okay. So you can say this is the true, right? This is the epsilon delta language. This is for any x in this interval. So now it becomes for some x in this interval. Okay. For any epsilon greater than 0 becomes there exists some epsilon greater than 0. There exists the delta greater than 0 becomes what? For any delta greater than 0. Such that for all x in this interval becomes for some x in this interval. This difference should be less than epsilon becomes greater than or equal to epsilon. Okay. Okay, so this is the does not satisfy, the meaning for does not satisfy. Okay, epsilon delta criteria. So now let's take, since this is true for any delta, right? Let's take this delta to be 1 over n. Right, we can do that. Let's take the delta to be 1 over from this definition. So there exists some xn such that 1 xn minus a is less than delta, which is 1 over n. But f of xn minus f of a should be greater than or equal to epsilon, right? This is what we have, right? We take here, since this the delta is arbitrary, so we take some specific number, 1 over n, right? 1 over n. So for 1 over n, so there must exist some x in this interval, right? We denote this x by xn, okay? So there exists some xn in this interval, then such that this f of xn minus f of a should be greater than epsilon, greater than or equal to epsilon, right? So you can see that 1 over n is a natural number. We can take n to be 1, 2, 3, 4, 5, and so on, right? Then from this choice, Then we can define a sequence xn, right? So xn minus a is always less than less than 1 over n. When n approaches infinity, this would be approaches 0, right? So that means xn will approaches a, right? Xn minus a will approach 0 when n is increasing, right? Becomes smaller and smaller. So xn, so this sequence is very close to a. The limit is a, right? So we defined a sequence xn which converges to the number a. Right? We define such a sequence. We define a sequence, right? Which converge to a. Why converge to a? Because you can see from this xn should satisfy this inequality, right? When n is large, the right side will approach 0. So the left side will also approach 0, right? The approach 0 means xn will approach a, right? When n is large, when n approaches infinity. So that means xn minus a will approach 0, so xn have the limit. The limit of xn is equal to a, right? So we see, so we using this way, we allow n take all the natural numbers. Then we can define a sequence xn using this way, right? And the sequence has the limit a. Okay. So by the assumption, so since xn will approach a, since f is continuous at a, then you have a sequence convergent to a. F is continuous, then f of xn minus f of a should be will approaches to f of a, right? Will approach to f of a, and n approaches infinity. So this is by the definition, right? Okay, then you can say this one, it contradicts that f of xn minus f of a should be greater than equal to epsilon. This is what we have, right? How do we define this xn? We define f of xn minus f of a is greater than epsilon, right? So it means this epsilon exists, right? Certain epsilon. So that means this C2 sequence, this sequence and this number is separated at least the epsilon, right? Epsilon is a fixed number. So it doesn't mean, it means it will not converge to A, right? The converge to A, that means when n is large enough and these two numbers would be very close to each other, right? So now it's separated by epsilon. So it does not converge to A. So this is the contradiction, right? So we have it converged to f of a, but this one tells you, okay, how do we construct this xn? We construct the xn by this f of xn minus f of a is greater than epsilon. That means f of xn does not converge to f of a. So this is the contradiction, right? This is the contradiction. This and this one is a contradiction. So since we have the contradiction, where the problem? The problem is we assume it does not satisfy. So in other words, so f satisfies the epsilon delta criterion at A. Okay, so this is the one direction. So keep in mind, when we talk about the if and only if problem, we need two directions, okay? So now let's look at the other direction. The other direction says, okay, so suppose we have the epsilon delta criterion holds for a function for the function f. Okay, so that means f satisfies the epsilon delta criterion at x equals a. So now let's so we want to prove this one is continuous. How do we prove it? We need to have a convergent sequence, right? Then f on that convergent sequence will also converge to f on that limit, right? This is the way. This is the definition we currently have. We want to prove this f is continuous. So we let xn be a sequence, of course, in its domain, in D, converging to A. We want to show that f of xn will approach f of A. This is our aim, right? Okay. So this is our aim. So now we want to use this one, right? We want to use this condition. Epsilon delta criterion holds for f. Okay, what does this mean? By the epsilon delta criterion at x equals a, we have for any epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of a should be less than epsilon for all x in this interval. X minus a is less than delta, not epsilon. Right. For all x in this interval. Okay. So this is what we have, right? We also have a sequence which has the limit a. So we want to convert this one to be our epsilon n language. Okay. So since xn has the limit a, then what does this mean? There exists a capital N greater than 0, such that xn minus a should be less than, okay, arbitrary epsilon, right? But here we have the epsilon already, so we don't want to show epsilon. But we can take this one. For any epsilon greater than 0, there exists a delta. Okay, for this delta, we must have some capital N such that this xn minus a is less than delta. No problem, right? For any epsilon, we take any epsilon to be this delta. Specific number to be this delta, okay? So since this one approaches A, then there exists the n greater than 0 such that xn minus a is less than delta. Delta is a number, right? Keep in mind this number should be arbitrary number, right? But here we just take this. This should be another epsilon, right? But we take that epsilon to be our delta. We can do that, right? No problem, because that epsilon is arbitrary. So we can take a specific number for our convenience, right? We pick that epsilon, this epsilon, to be our delta, okay? For all n is greater than equal to epsilon, capital N. So for this n, because this is true when x in this interval, f of x minus f of a must be less than epsilon, right? This is the thing we already know, right? This is epsilon delta. Okay, so now our xn is also in this interval, right? Xn minus a is less than delta. This is the same interval, right? So Xn should also satisfy this inequality. Right? This is true for all x. Right? All x in this interval, it must be this inequality. Now our Xn minus a is less than delta. So Xn is inside. All right? Xn is inside. So f of Xn must be minus f of a must be less than epsilon. So f of xn minus f of a should be less than epsilon for all n greater than equal to capital N, right? Because when n is greater than equal to capital N, then we have this xn minus a. The distance between xn and a is less than delta. Then the distance of the f values would be less than epsilon, right? This is from the epsilon delta criteria. When x, the distance between a and x is less than delta, then the distance of the function values will be less than epsilon. So now our xn, when n is greater than capital N, then the xn, the distance between xn and a would be less than delta. So that means this xn lies in this interval. So it must satisfy this inequality. So we have this one, right? This is true for n is greater than capital N. So what does this mean? This means f of xn minus f of a. We approach f of a. Why? This is the definition of the sequence, the limit for a sequence. Right? Why? Because you can see for any epsilon greater than 0, there exists a capital N. F of xn minus f of a is less than epsilon for all n is greater than capital N. Right? That is the exact definition for f of xn has the limit f of a. Right? This is the sequence. Right? This one is a sequence. This one is a sequence. Right? The definition for the sequence. Right? For any epsilon greater than 0, there exists a capital N. When n is greater than or equal to this capital N, f of n, that sequence minus the limit would be less than epsilon, right? Okay. The only trick play here is instead of using arbitrary epsilon, we take that arbitrary epsilon to be the specific number, which is delta here, this delta. Okay, the same delta here. Right? The reason is we want to have this inequality. We want our x should be in this interval. So we take this delta. Right? Okay. So this is the definition. So this theorem tells you one thing is f is continuous if and only if for any epsilon greater than 0, there exists delta such that x minus a is less than delta. When x in this interval, f of x minus f of a would be less than epsilon. Okay? You should be very familiar with this language. Okay, so now let's look at another remark. So this epsilon in continuity, the choice of delta depends on this epsilon and A, right? Why? This is the definition, new definition, right? You can see there exists delta. This x minus A is less than delta. So that means the distance between x and A is less than delta. So this delta should be the choice. The choice of delta depends on the choice of A, right? Okay, then the function value will less than epsilon. In other words, this delta will also be the choice. The choice of delta will also depends on the choice of epsilon. So we can say this delta is actually depending on the choice of A and the choice of epsilon. Okay. So now we have another one, which is called the uniform continuity, right? The uniform continuity says, okay, this epsilon, this delta, the choice of delta only depends on the epsilon. Has nothing to do with the position, okay? Uniform continuity. So we just quickly recall the definition for the uniform continuity. Okay, we say, okay, recall the definition. What's the uniform continuity say? Okay, if f function f is from D to R, is called the uniformly continuous. Uniformly continuous. On the domain D, if whenever two sequences UN and Vn, which is in the domain D, such that the limit n approaches infinity of f of un minus f of vn should be equal to 0 if this un and the vn take the limit of the difference would be 0, right? This is the definition for the uniform continuity we use in the sequence. So this definition, we say, okay, we know that remark. I didn't say with any point, right? We just say it's uniformly on the domain. So any points on the domain. So in other words, this delta depends on. Okay, sorry, I didn't see that. I should have given you another one. Another definition. Okay, so this is the definition we have learned in the when we first studied the uniform continuity. So now let me give you the epsilon criteria. Okay, on the whole domain, we have the epsilon criteria on one point, right, at A. So now let's see another definition, which is F is D to R, okay, is that satisfies the epsilon delta criterion on the domain D if for any epsilon greater than 0, there exists a delta greater than 0, such that f of u minus f of v is less than epsilon for u and minus v. The difference, the distance and u and v is less than delta. And uv are in the domain D. Okay. So we say this function satisfy the epsilon delta criteria on the domain D, on the whole domain, which means for any epsilon greater than 0, there exists a delta greater than 0, such that when 2 points in the domain D are very close, how close it? It's close less than delta. Then the function values will be very close. How close it? The difference is less than epsilon, right? So here is the math language for this epsilon delta criteria, right? We often say, okay, if they are close enough, how close enough? We use this inequality to represent the closeness, okay, of two quantities. We should be very careful, precise, right, for the language. We often say, okay, in your calculus, we often say it's close enough, we're large enough. How large is called large enough, right? It's greater than a certain number, it's called large enough. How close is, it should be less than certain numbers, right? Okay. So then we have the theorem. So we will not prove the theorem because the proof would be exact, almost exact same. Okay. F is uniformly continuous on the domain D if and only if this F satisfies the epsilon delta criterion on the domain D. The proof almost exact the same as the previous theorem. For the continuous function is continuous at a certain point, right? So now it becomes uniformly continuous on the whole domain D. Okay. Now let's look at the remark. So the remark, the first remark said, okay, this theorem actually gives you another definition for the uniform continuity. Okay, so new definition. Of uniform continuity uniform continuity. Okay. So we say function f is uniformly continuous on the domain D if for any epsilon greater than 0, there exists some delta greater than 0 such that this f of u minus f of v should be less than epsilon for u minus v is less than delta. Okay, we don't need to say, okay, u v must be in D because we need to calculate f of u, f of v, right? So u v must be inside D. Otherwise, it's undefined, right? This is the new definition. So from your homework, okay, in the 3.3, I remember, or 3.4. From your homework, I noticed that some students already using this definition, okay, to prove the uniform continuity. Right? Some students already using this definition, not using the definition from the sequence. Okay, that's okay because it's true, right? So some students already using this definition. they take specific delta such that this one would be less than epsilon. Then we say, okay, it's uniform continuous. Okay, so you can say that this epsilon, the second, this epsilon has nothing to do with the positions, right? We just need the UV inside the domain. So it has nothing to do, we just need to be close to each other, right? How close? Less than delta. So this delta has nothing to do with the positions, but only depends on the choice of epsilon, okay? 2. So now, look at these two definitions, right? This is the continuous at A. It's a continuous at A. For any epsilon greater than 0, there is a delta such that for x minus A is less than delta, then this f of x minus f would be less than epsilon. So here is f is uniformly continuous on D if for any epsilon greater than 0, there exists a delta such that f of u minus f of v is less than epsilon for u and v is less than minus u minus v is less than delta. So what is the difference? The difference between continuity and uniform continuity using this epsilon delta criteria. What's the difference? Okay, we know the statement is a little bit different, right? How can we see that on the graph? Okay, so let's look at this one. We have a very flat, smooth curve. Okay, so this is y equals f. We denote f1, okay? Uniformly continuous. On the domain D, on the domain AB, okay? So if this is A and this is B, what does this mean? This means for any epsilon, for this epsilon, okay? So the difference is this delta depends on only on epsilon, okay? So what does this mean? This means if you draw a box, if you have a box, okay, the height is epsilon, okay, O2 epsilon. This is epsilon, right? The height is epsilon. The base is delta, right? Then this epsilon can determine the base delta. If epsilon is given, then you can always have this delta such that on this box, the curve enter the box from the one side, then leave the box from the other side, not from the top and the bottom, right? Otherwise, it will not less than epsilon, right? And this box is uniform. You can always have this box, the same box, epsilon delta, for anywhere. The same box, okay? The same box. You can use the same box, put this same box on anywhere on the curve, okay? It always be, of course, this is the center, okay, not meant. It always makes this curve enter this box from the one side and left this box from the other side. So that means this box has nothing to do with the positions. Okay, you can put the box here, right? The same box, you can put the box here, the same box here. But for the continuity, this is the one last time we say, okay, it's not uniformly continuous, right? Because it's steep. The steepness increased fast, right? So this, but it's continuous, no problem, right? This one is continuous. But you're not uniformly continuous. But not uniform. Why? For example, if the point is here, you can always draw a box, right? If the epsilon is given, you can always draw the box. This is epsilon, this is delta, right? Epsilon delta box. If the point is here, if A is here, if A is here, you need to draw a box to make this curve enter from one side and leaving from the other side, right? So you must have, you cannot use the same box. You must have draw this box, right? If epsilon is given. If this is epsilon and this would be the delta. If A is here, actually you need to draw a very thin box. This is epsilon, this is delta. Right? So you can see the box, the size of the box is different. But for the uniform continuity, we can use the same box. If epsilon is given, this box will be fixed. For this one, it's continuous, but not uniformly. So that means for epsilon is given, the delta cannot be determined because it will change also depending on the position of A. Okay, so this is the difference. You cannot use a uniform box to make this curve end the box on one side and leaving the box on the other side. You have to adjust, okay, the box. So it's continuous, but not uniformly. So you can see the difference, right? So now, let's look at another one. So last time, not last time, previous section, we have the theorem said, okay, if you have a continuous function on a closed interval, then that continuous function must be uniformly continuous, right? So a closed interval, a continuous function on a closed interval, then the uniform continuous and the continuity are exactly the same thing. Okay, that theorem tells you that. So now we want to prove that, we want to show that this function f of x, which is x cubed, okay, we know x cubed is very steep, right, for the slope in somewhere, is uniformly, okay, continuous on the closed interval from 0 to 20. No problem, right? So we want to show that. How do we show that? We want to use the epsilon delta criterion, okay? This is a good practice by using the epsilon delta criterion. So in your homework, in this section, for any continuity or any uniform continuity, you need to use the epsilon delta criterion to prove it. Okay, don't use other theorems. Okay, you cannot say, okay, it's continuous, so it's on the closed interval, it's uniform, then we're done. Of course, you're right? But our aim is ask you to practice, right? Practice the epsilon delta criterion. So the steps are very similar. We still need to look at f of u minus f of v, right? We still need to look at what's that? That is u cubed minus v cubed, right? The same thing, we need to factor out u minus v, right? Because our definition says, okay, we need this u minus v, right? U minus v. So we factor out u minus v. So we have the formula, right, for this one, which is u minus v times the absolute value of u squared plus v times u plus v squared. Right. We take the absolute value for each term. Okay, I just skip one term, one step. So since this is on this interval, right? If we replace this one with so this term can take the largest number, which is u and v is equal to 20, right? So it's less than equal to, if we plug in 20 for u and 20 for v, you add together, it would be 1,200. You have this one. Okay, so we want to take this one to be less than epsilon, right? So we, for any epsilon greater than 0, there exists, this one should be less than delta, right? So 1,200 delta is less than epsilon. So this delta we should take to be epsilon over 1,200, right? So we take, there exists a delta. What is this delta? This delta is epsilon over 100 to 1,200, okay, such that when u minus v is less than delta, this is f of u minus f of v. We just calculate. It's less than 1,200 times u minus v, which is less than delta. This one less than delta, so it's less than 1,200 times epsilon over 1,200, which is equal to epsilon. So we are done. Right? So you can see for any epsilon greater than 0, there exists a delta, which is of course greater than 0, such that u minus v is less than delta, f of u minus f of v is less than this epsilon. Right? So this is the exact same. Okay. So the convenience for the uniform continuity, the interval is given, right? Not like the continuity. Remember, for the continuity, we needed to make our own intervals, right? To enlarge this one by a certain constant, right? To bound this term by a certain constant. So this is the difference. Okay, so this is the section. This section, we finished this section. Let's continue to our next section. The next section is the which is about the monotone functions or inverse functions and inverse functions. Okay. We will study the monotone functions and the inverse functions. So why we talk about the monotone functions? So we have the monotone sequence, right? Right, sequence is a numbers, right? Discrete numbers. But if we connect these numbers together, we will form a function, right? Function is a continuous function. We have a function, some curve, and we want to extend the monotone sequence to our monotone function. Okay. So what's the, so first I give you the definition for the monotone functions. So we suppose that our f is a function from D to R. Okay. We say that a function f is monotonically increasing if f of A is less than or equal to f of B for A is less than B. A is less than B, then f of A is less than or equal to f of B. It's called monotonically increasing. We say f is monotonically decreasing if f of A is greater than or equal to f of B for A is less than B. Okay. It's called monotonically decreasing. We say a function f is either monotonically a function that is either monotonically increasing or monotonically decreasing. This function is said to be monotone. This kind of function is called a monotone function, which is either monotonically increasing or monotonically decreasing. Monotone. It's called a monotone function. Okay. If the inequalities here without any equal sign, okay, are true without any equal sign. So that means f of A less than f of B, f of A greater than f of B. Then we say F is strictly increasing or strictly decreasing. Okay, this is another definition for the strictly increasing and strictly decreasing. Now let's look at, let me see if we have time to prove the theorem. Okay, yeah, I can state the theorem first, okay, then I talk about the theorem first, then we can prove it next time. .23. Suppose F, which is from D to R, is monotone. Okay. I didn't say this one is continuous, okay? I just say it's monotone. If, so on what kind of condition this one would be continuous? Is that, okay, if the image f of D is an interval, then F is continuous. Right? Do you remember we have a theorem? If a function is continuous and the domain is an interval, then the image is an interval, right? We have that. That is different from this one, okay? This one says, okay, F is monotone. The image is an interval. I didn't say this D is what is an interval, okay? I didn't say this D is an interval. I say this F is continuous, then FD is an interval. Then F is continuous, okay? F is continuous. So since this is a monotone, so monotone means two things, right? Either monotonically increasing or monotonically decreasing, okay? So here we only consider the case for the F is monotonically increasing. Why we do that? Because for the case that F is monotonically decreasing, we can always take the negative F, right? If F is monotonically decreasing, so the negative F would be monotonically increasing, right? We can use the same way to prove negative F is true, right? If F is a function, we know negative F is also a function. If F is continuous, so the negative F would be continuous, right? So if we can prove that the negative F is continuous for the monotonically decreasing, then negative F is continuous. Then we can say, okay. Yeah, I would say if F is negative monotonically decreasing, we can take the negative F, right? Then the negative F would be monotonically increasing. If we can prove the case for monotonically increasing, then we say, okay, negative F would be continuous, right? So negative F is continuous, F must be continuous. Okay, so for the proof, we only consider the case where F is monotonically increasing, not monotonically decreasing. Okay, the reason is that the negative F would be monotonically increasing. Then we can prove the negative F, right? Then go back to F. Okay, before the proof, let's look at one example. Okay, The next time we will prove this theorem. So this example says monotonicity. You cannot, this would not be true if this function is not monotone. Okay. Monotonicity is required for this theorem. For example, f, which is from R to R, okay, is defined by this way. F of x equals x when x is less than or equal to 0, equals 1x minus 1 when x is greater than 0. Okay. So the graph will look like this one. Less than or equal to 0 is x. Greater than 0 would be 1 minus x, if this is the 1. This is the graph for this function. So here, f of 0 equals 0, right, from this graph. And what is the range? What is f of r? The domain is OR, right? All x values can have the points corresponding to it. What is the range? Range is the value of y values, right? So you can say all the y values can be taken, right? So the range is also R. R is from negative infinity to infinity, so which is an interval, right? Which is an interval. But this one, this f is not monotone. Why? Because you can see if x values takes here, right? Which is greater than x value takes here. X value takes here is less than this x value takes here, right? So it's not monotone, right? Sometimes it's greater than, sometimes it's less than, right? So it's not monotone. And so if you without this monotonicity here, even the image is an interval. You cannot say this one is continuous because you can say this one is not continuous at x equals 0, right? This function f is not continuous at x equals 0, right? So you can say from this example, the monotonicity is required in this theorem. Okay, so we stop here, and then next time we want to start to prove this theorem. Okay. Any questions for this topic?